Okay, in this video for Algebra 2, we're going to continue to practice with the quadratic formula. We spent some time last week introducing the quadratic formula, and we noted that if we understand our a, b, and c values for a quadratic equation that's equal to 0, we should be able to use a calculator to evaluate the results of that quadratic equation. Now, we set up our calculators last week to look something like this, where we defined QFP and QFM for the quadratic formula with a plus sign and quadratic formula with the minus sign. So both of these equations are representations of the quadratic formula, where the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a determines our x values, or our variable results, based on the given information inside the quadratic formula. Inside of the quadratic equation. So we have our calculator set up for that now. I would like to talk just a little bit further, because we haven't seen them yet, but there's a possibility that we will, that our calculators will actually return an error message to us when we try to use them to solve a problem. Now, a problem might arise because of the square root symbol. Inside the quadratic formula, we have a section that requires b squared minus 4ac to be placed underneath a square root sign. Now, we should recognize that the square root of negative numbers are not possible to complete in the real number system. We need what we call complex numbers or imaginary numbers. So that we can be better prepared to handle those, I suggest making one alteration to the quadratic formula. Instead of stating that the result of our equation is equal to the opposite of b plus or minus the square root of b squared minus 4ac, let's say that it's plus or minus the square root of d divided by 2a, where we calculate d as a preliminary computation ahead of time before we begin. Our understanding of this d value, which we call in mathematics the discriminant, will let us predict what type of answers we'll see inside our quadratic equations. So for practice, we're going to spend some time identifying a, b, c, and d for these equations. And the first one has already been completed, although it's a little bit out of order. So let's jump down here. This 11b squared minus 22 minus equals negative 7b. Is that how that was set up? Yeah, equals 7b. Sorry, I misread the problem originally. Equals negative 7b. That's how the original problem started, so let's see how we would have used the quadratic formula to approach it. Well, right off the bat we see that this negative 7b is over here on an island by itself, so we better bring that over to the left by adding it on both sides of the equation. That turns into a positive 7b in this location. Now we know our a, b, and c values are provided because we have a quadratic equation now set equal to 0, and that's the requirement for the quadratic equation. If we calculate our discriminant d value ahead of time, and we define that as b squared minus 4ac, then after substituting and simplifying, we see that our discriminant, or d value in this case, ends up equaling 1017. So I would report my a value as 11, b value as positive 7, and c value as negative 22, and we can compute our discriminant, or d value, to be 1017. Now that we've done that preliminary work, we don't really need the entire quadratic formula that's set up this way. We can actually jump straight to this format here. And in the event that we have to simplify this expression by hand, I think this format's a little bit easier to do. We can find the square root of 1017 simplified, and we'll talk about that technique in class if needed. We can simplify the square root of 1017 into 3 times the square root of 113. And now we actually have two solutions in this box right here. Negative 7 plus 3 times the square root of 113 divided by 22, and negative 7 minus 3 times the square root of 113 divided by 22. Now, if the calculator can give us a real number answer, sometimes it is easier to basically take the quadratic formula and our defined quadratic program on our calculator and just go straight to these answers. but there will be some times where we need more precise results, and we'd rather see our result in this radical form. So let's jump off to the side here and try a couple of these examples. Maybe we won't do all of them, but maybe we'll complete a few of them here. Let's try these 4. Now, I don't have a whole lot of room on my screen right here, so I'm going to slide over to some lined paper portion, and we'll work on them here. Okay, so I've got them set up over here, and hopefully we have enough room with 5 or 6 lines in between. Let's see what we can do to work through them. Now again, I'd like to calculate my discriminant value. So first I'll need my A, B, and C values. And since I have a quadratic expression equal to 0, I know that I can identify my A values, B values, and C values pretty easily. So A is 12, B is 9, and C is also positive 9. My discriminant was described as b squared minus 4ac, which would be the square root of 9 squared, this 9 from the b value, minus 4 times our a value, times c, our value of 9. And sorry, I made a mistake here. The discriminant does not include the square root sign. We just want the number that's underneath the radical. So I'll calculate my discriminant this way. Now, we could continue to do this by hand, but since a calculator might be necessary anyway, let's go ahead and compute this one with the calculator. And as long as I can recreate this expression in my calculator, I'll trust that the calculator is going through the order of operations correctly. So I have the 9 squared minus 4 times 16 times 9. I'll tap enter and I get the number negative 495. Now this is interesting because I had stated that the solution, x, is going to be the result of the opposite of b, our 9 value, plus and minus the square root of now our d value, our discriminant, which is negative 495. And we'll divide that by 2 times a, or 2 times 12. Now, unfortunately, since we're being asked to take the square root of a negative number, this will not be computable with a basic calculator. There are no real number solutions. Since we've built this formula into our calculator, however, if you've got a calculator that has this chaos model here, then this calculator can actually execute this and produce an imaginary number or complex number solution for us. So just out of curiosity, I'm going to run the QFP formula with the A value of 12, B value of 9, and C value of 9. And we can see the result here. It's not a typical number. It contains this strange I. And if we ran QFM, the quadratic formula with the minus sign, I think we'll also see a similarly strange result. So QFM with those A, B, and C values also produces a weird looking result. At this point in the class, we're not going to dwell on what this I value means. We just need to note that this is a non-real solution, or what we would call an imaginary number or complex number solution. So what I'm going to do is I'm just going to report that there are no real number solutions for it. In this example over here, we will approach it much the same way, except let's note that we don't have an equation equal to 0. So the first thing that we must do is make this equation equal to 0. I'm going to do so by subtracting 7x from both sides of the equation. Sorry, it's getting a little bit tight there, but 3x squared minus 7x minus 26 will then be equal to 0 because they canceled out over here. And now I can identify my A, B, and C values. So A is 3, B is negative 7, and C is negative 26. Our D value, or discriminant, needs to be B squared minus 4 times A times C, which in this case is negative 7 quantity squared. So this negative 7 is going to multiply itself and make a positive 49, by the way. Minus 4 times 3 times negative 26. And if you're looking ahead or thinking about this critically, you'll note that this negative 7 squared becomes a positive number But then also this negative 4 times negative 26 is also going to become a positive number. So while it looks like this may end up being negative because of the negative signs, in actuality I would expect this result to come out to be positive. So let's take a look. If I use my parentheses with negative 7 and I square that on the outside and subtract 4 times our A value of 3 and our C value of negative 26, and when I press enter here, we can see the discriminant result, which is 361. I don't know what the answers are just yet, but I do believe that we will get some fine answers because the solution for x must be the opposite of negative 7 plus or minus the square root of 361, and all of that divided by 2 times our A value of 3. When simplified, this double negative turns into a positive number, so positive 7. The square root of 361 ended up being really nice. That's 19. Whoops. Negative 7 plus and minus 19, because that's the square root of 361, and all of that divided by 6, because that's 2 times 3. Well, 7 plus 19, that's something that we can figure out. That's 26. And 7 minus 19, that's not too bad. That's negative 12 divided by 6. And 26 divided by 6, I think that's going to come out to be a decimal. That's 4 1/3 maybe, so 4.3 repeating. And we also have negative 12 divided by 6 is negative 2. Let's go ahead and check that with the calculator real quick. But in fact, I think what I'll do is I'll enter this. Oh, what the heck. Let's go back to the beginning. If we're going to use the calculator, we might as well use it all the way back here. So let's go ahead and do that. We'll run this twice. I'm going to create a fraction by control divide. And we had a negative 7 plus the square root of 361, all divided by 2 times A, which was 3. There's that 13/3, or if I press Control Enter, the 4 1/3 repeating. And if I repeat this calculation again with a minus sign in between, we end up with the negative 2. So the answers that we got by hand end up agreeing with what we've got on the calculator, but let's go ahead and check what QFP and what QFM produces. So if I use Quadratic Formula plus that formula, or that program that we wrote in the calculator, with an A value of, what did we say, 3, a B value of negative 7, and a C value of negative 26, we end up getting that 13/3, or 4.3 result. If we run the QFM formula, quadratic formula with a subtraction, quadratic formula with a minus sign, so QFM, we end up getting the negative 2. So as it turns out, it doesn't matter which technique we use, whether we use the QFP formula and QFM formula, or if we solve by hand, we appear to be getting the same result. Now again, for observation's sake, this discriminant value ended up being a positive number, and we got 2 real number solutions. When our discriminant over here was negative, we had no real number solutions. Let's try this next example. Here we have an A value of 1, a B value of 6, and a C value of 9. Our D value would be B squared minus 4 times A times C. I can do this one in my head, actually. This is 36 minus 36. That comes out to be 0. Okay, well, I know what happens when our discriminant's positive and when it's negative, but what happens when the discriminant comes out to be 0? Just not quite sure. Well, let's see. If I was going to solve this, I would use this new formula now that I have the discriminant, and I would say that my result for x is equal to the opposite of b plus or minus the square root of d, discriminant, divided by 2 times a, which is 1. Well, that's kind of neat because the square root of 0 is 0, and negative 6 plus 0, negative 6 minus 0 is the same thing. So I now have negative 6 divided by 2, or in other words, negative 3 as the result. And so that implies that negative 3 is the result for the quadratic formula plus and the quadratic formula minus technique. So let's see what we get. What is QFP with 1, 6, and 9? Let's check this one out. We'll take a look at it. So QFP with 1, 6, and 9 as our coefficients. We ended up getting negative 3. That's what we would expect. And QFM also comes out to be negative 3. So that ends up matching what we've got here. And as it turns out, that observation is indeed true. When our discriminant ends up equaling 0, we had just one solution. It was technically two solutions that ended up being the same value. So we can call that one real solution. Let's go ahead and do this last example, and then we'll finish up and summarize the video. Here again, we would like to have a quadratic function equal to 0. So I think I would like to add 9r to both sides and subtract 10 from both sides. If we add 9r to both sides and subtract 10, that means they're going to cancel themselves out on the right side, and we'll be left with the number 0. And on the left side, in this case, we'll have a 10. We'll have a positive 1r, and then we'll have an 11r squared that was untouched. And now we can identify our a, b, and c values since we have an equation equal to 0. A is 11, b is 1, c is 10. So our discriminant would be b squared, so 1 squared minus 4ac, or 4 times 11 times 10. Now I can already tell that there's going to be a problem here. We've got 1 squared, which is 1, but now I'm going to subtract 4 times 10 times 11, and that comes out to be 440. So we have 1 minus 440, or in other words, negative 439. So what's to be expected when we encounter a negative discriminant? I suspect that there's going to be no real number solutions. And let's see what the QFP and QFM produces. So QFP, quadratic formula plus. What did we say? Our A value was 11, B was 1, and C was 10. 11, 1, and 10. 11, 1, 10. Sure enough, we get an imaginary solution, and if we run QFM with the same A, B, and C values, so QFM, we also get another imaginary number solution. And even if we had set this up using the shortcut form of the solution, the variable, which is r in this case, is equal to the opposite of b plus or minus the square root of negative 439, our discriminant, divided by 2 times 11. And here again, that just can't be simplified. We don't have a technique yet to handle the square root of negative 439. So if we wanted to summarize what we found here, is that when the discriminant value comes out to be positive, that generates two real number solutions. Two real number solutions. And these solutions could be decimals, fractions, whole numbers, you name it. But we'll have two numbers that we can find on a number line. When the discriminant is negative, we found that there are no real number solutions. So at this point in the class, we have basically nothing that we can do. But what we will learn is that this actually turns into two complex solutions as we get further along in this class. When the discriminant comes out to be 0, I guess in a sense we did get two real number solutions again, but these two solutions ended up being the exact same number. So most of the time we'll just report this as one real number solution. So if we take the time to compute our discriminant ahead of time before we actually find the solutions and rely on our calculator to give us a result, we can learn whether or not the solutions will be real numbers or complex numbers before we even begin, or before we get too far anyway. I think in the interest of time, I'm not going to run through these quadratic formula examples with decimals, but I would like you to know that part of the reason why the quadratic formula was established is so that we can handle equations very similar to this. If we encounter a, b, and c values that have decimals or fractions in them, we can feed that to our calculator and or the discriminant computation, and we can move forward from there. But again, I think we should just save these for another time. If you have any questions, please let me know, and otherwise I'll just see you all in class. Thanks for watching.